Hello, everybody. I hope you've enjoyed the first talk of the virtual summit, MRMIA. I'm Alan Forrest. I'm a board member of the Model Risk Managers International Association, and I'm very pleased this morning in the US. It's afternoon here in Edinburgh. Very pleased to introduce Jonathan Crook, who is Emeritus Professor of Business Economics at the Business School at the University of Edinburgh. Emeritus means he deserves it, and he has a long career in economics and business economics, which has taken him to the States, the University of Virginia, as a postdoctoral research scholar, and also to the Wharton School at the University of Pennsylvania. Recently, he is founding director of the Credit Research Centre at the University of Edinburgh Business School, and has many fellowships and memberships to his name. I won't occupy more of his valuable time, but simply give the stage to Jonathan on climate models and their model risks. So thank you very much, Jonathan. Please go ahead.
Thank you, Alan. Whoops. Okay. Well, thank you very much, everybody, for tuning into this one. And thank you very much to Alan and to Joe for asking me to do a talk on this. I should put in the usual caveat, this is work in progress, except this really is work in progress. And you'll see what I mean as we go through. Like Joe, I've got too many slides. So basically the connection between what I'm going to talk about and model risk is this. If you don't include extreme weather events in your underwriting models, credit scoring models, I'm going to show you what will happen to AUC, and I'm going to show you what might happen to the amount of capital, economic capital, that you might wish to hold. In both cases, if you don't include, as you'd expect me to say, the AUC, we find will be lower, and the amount of capital, economic capital, that you think you want might be underestimated. So that's the bottom line if I don't finish. Okay, so we're going to look at whether including weather events for mortgage into credit scoring models for mortgage loans actually enhances predictive accuracy. The answer is yes. And then we're going to examine the effects on economic capital, and the answer is it increases it. Okay, so first of all, let me say that the requirements of many central banks are that one should include climate risk in your credit risk models. Here's some quotes. Bank of England, banks should integrate climate risk related risks in both their own credit risk assessment and at the level of individual exposures. They should also assess climate related risks. European Central Bank, climate related and environmental risks are expected to be included in all relevant stages of the credit granting process. And then up until October 2025, the OCC and FDIC said that management should consider climate-related financial risks as part of the underwriting and ongoing monitoring of portfolios. And indeed, in 2023, the FRB carried out a climate scenario analysis, which I'm sure many of you are familiar with. In October 25, these principles were withdrawn. Okay, now, if you do some reading in this, you come across literature which is often quoted, but it actually isn't that relevant to what I'm going to talk about. So I'm going to put a line between two things. First of all, there are many papers which look at whether or not severe climate events cause a change in PD. These do not give you predictions of PD. They have very simple treatment of covariates. They only relate to specific events. In other words, at specific times in specific locations. So they're not really comparable with what we're talking about. What we're talking about here are credit scoring models which give predictions. We're looking at over time as well as between individuals. So it's panel data. And in this context, that means survival models. In other words, the probability that default will occur for the first time in the next time period, which is typically a month. There are several papers here. and I commend them to you. They're really, really well done. They often model default, sometimes prepayment as well. They have fairly sophisticated, at least one or two of them do have sophisticated treatment of covariates, some of them don't. They do include measures of predictive accuracy, and they do include macroeconomic variables, and these are often many differences compared to these earlier papers as well. So here is the transmission mechanism that we're going to be thinking about. We're going to be talking about physical risks, and we're going to concentrate on wildfires and or high temperatures, the argument being that wildfires together with high temperatures cause more damage. Low precipitation, so if there's drought and wildfire, even worse damage. If there are high winds, worse again, and so on. So wildfires probably interacting with these other climate severe weather events lead to damage to places of employment, so loss of income. There may be health impacts, loss of income for that reason, but the main transmission mechanism is usually reckoned to be property damage. This lowers house prices, raises the LTV, and so defaults go up. There's a little bit of techie stuff. I will keep it brief and do a lot of, I would say arm waving, but you can't see. But anyway, I'll explain what's going on in intuitive ways. So we're thinking about a survival model. Q, think of it as the probability that the event, i.e. default, will happen given that it's not happened before. And we're going to say what drives this probability are standard things, characteristics of the borrower, characteristics of the property, these X variables. Then the state of the economy, a lot of literature on that now, will also be involved. And we're going to include weather variables, some others have, but not quite like we have, and the location represented by the latitude and longitude of the property, hence I, because the loan is related to a property, and how long the account's been open, and that's just duration time in a standard survival model context. So we're going to represent standard credit scoring models as the X, latitude and longitude. I'm not going to say much about that today. Then we've got macro variables, which is the Z, and the weather variables, which are the W. Okay, so here is, I guess, things that may be a bit unusual, but is now increasingly being introduced at the cutting edge of statistical models and credit scoring. That model I just showed you is linear. The relationship between many of the drivers and PD is linear, but there's a lot of evidence. It didn't just start with this one, and we put a paper in Nature in 2019 that shows it as well. These relationships are not really linear, and indeed the whole point of using machine learning methods that Joe was talking about is because the relationships are not linear. So we're in a statistical context, and we're going to consider very, very flexible functions that relate weather variables to PD. And these flexible functions are very smooth, hence this bit here. S actually stands for spline, but if you want to think of it as smooth, that's fine by me. So we've got the same model, but we've got a smooth on weather. Now, I need to say something about splines because many of you may not be, I apologize for those that are that familiar. Basis splines, known as B-splines, consist of bits of polynomial functions. So here we've got a variable x. Okay, just concentrate on the left right now. If we say that the value of x, when it's between these two values, when it's in this range, the value of another variable, y, say PD, and this might be income, for example, is related in a polynomial way. We might think of it as x squared, but we might think of it as a fairly complicated cubic. That's joined in the next range by another piece, which is typically, in our case, is going to be cubic. This one actually shows a quadratic because it's easier to draw it. And then there's another piece here, which is also a polynomial. Again, whoops, in this case, it's a quadratic. Now, it turns out that the actual parameters of each of these pieces, we don't need to estimate. All we need to know, all we need to decide are the places where these pieces join, the so-called knots, the range over which this bit of function applies, this bit of function applies, and this bit of function applies. Those ranges, and whether it's a quadratic or a cubic, and most people now use cubics, that's enough. What we do estimate are these thetas. So each of these is a basis spline. We don't need to know exactly what the parameters are in here. All we have to say is where the knots are. All we have to say is whether it's a cubic or a quadratic. We use cubic. All we then need to do is estimate these thetas. And if we go back one, if I can, all we're doing is adding these up. Now, you might think if you add them up, you're always going to get the same number. Not so, because each of these would be weighted by a different number, which is determined by the data. And that allows you to have a very smooth relationship, which could be very, very wiggly indeed, and potentially could overtrain, though we stop that in the estimation method. Okay. So how are we going to use this? Well, the Federal Reserve Board's pilot climate scenario analysis, which I referred to earlier, 2023, found when it looked at the largest 6 banks in the US, how did they come up with a weather scenario? How do they come up with the effects on capital? They found that the banks assumed historical relationships between inputs and outputs continued to hold as the climate and structure of the economy evolve. This seems kind of unlikely. We've got a lot of data over a long period of time, and even over a short period of time, the economy is evolving all the time. The climate, according to many, is changing over time. So we need to represent this possibility. So what we do is we allow the coefficients on a weather variable to vary over time. Excuse me. So we've got a smooth here, which is on the actual coefficient on weather. Then we could make this a function of time, saying that the coefficient on weather varies over time. And then another thing we could do is we could say, well, this is another variable altogether. And we look at the bivariate relationship between these two. And what I'm going to show you, and you can relax, I'm going to do it in diagrams, is show you the result of estimating this model in this way. Okay, so we could have time varying coefficients on here. The coefficient, the effectiveness of W on PD varies over time in a way that we're going to estimate. It could vary according to another variable, like if we're thinking about wildfires, wind speed or temperature. And it could vary in a fundamental way where they're both varying, not just the coefficient. Okay, so we're going to look at those three things. Okay, so the final model consists of a linear combination of variables, sort of thing you're used to. These flexible functions of individual covariates added, weather variables, which I'm going to look at 4 of them, and a very flexible, smooth function of 2 variables which covary together. Okay, so that's the end of the maths. Now, let's think about what variables we're going to put in there. Well, it's been informed by the literature, credit scoring work, also papers in this area, papers in the literature. So the data we're going to use, and I'll be a bit more specific soon, is the Freddie Mac, a single loan family data set for mortgages. So application variables that you'll all be familiar with. We're going to look at a large number, or we did look at a large number of macroeconomic and weather variables, and we selected the ones using experimentation, basically to find the ones with the highest significance. So the sort of characteristics we've got for characteristics of the borrower, and there are some of the particular property as well, are these. The macroeconomic variables that survived the stepwise routine ended up being these: the unemployment rate, consumer confidence, interest rate spread, which is the actual interest rate on the loan minus the 30-year interest rate average from Freddie Mac. Now, I'll be a bit slower over the weather variables because one of the ones we've chosen after a lot of experimentation is what's known as the Palmer Drought Severity Index. And basically, it's a measure of drought. It's basically saying what's the difference between precipitation and the amount of evaporation out of the soil. There is a water balance model which predicts the evaporation. The things to know about it is that it's a deviation from the norm in that area. So plus 10 is the limit of meaning extremely wet, minus 10 is extremely dry. And it's cumulative in the sense that it doesn't jerk around month by month. It depends also on previous values, which kind of what you'd expect because water just doesn't evaporate immediately. Okay, so it's a measure of drought. The other variables we're going to look at is temperature, the argument being that if wildfires occur and the temperature is very high, they're likely to be more difficult to put out and cause more damage. I've talked about the Palmer's PDSI. Wind speed, if you have a wildfire and the wind is high, then obviously it will spread more rapidly and cause more damage. And then the measure of wildfires is just the number. I'm putting this in because in case people want to try and replicate or introduce these sorts of variables. There are a number of things you've got to put together. First of all the data's got to be available monthly. Most of it is, well, actually all of this stuff is. But it's all got to be available at the same geographic granularity, and that's more of a challenge. Now, as academics, we had only access to the Freddie Mac data, which is available at 3-digit zip. Okay. The drought index is only available at county level, but using weighted averages by population, we could convert that to 3-digit zip. Temperature the same. Wind speed is available to 30-meter square grids. I should add that we're looking here at California, which is what the CA obviously stands for. And obviously that's a good one to look at as far as wildfires go. For the data for wildfires, it's only available for the whole of California, so we couldn't transfer it to 3-digit zip, but it does vary over time. Latitude and longitudes in digits at the centroid of the 3-digit zip, and macroeconomic variables at the state level of California, so they're also varying only over time. The data we've got relates to mortgage accounts originated between 1999 and 2024, and we define default as 90 plus TBD. So here are some results. Now, here's a linear model, the baseline, in other words, the combination of longitude, latitude, and duration time is actually a spline, it's a smooth. So I haven't put that in, but the crucial thing to look at is not so much this, although all the signs are what you'd expect, but on the right-hand side. So here we've got the drought index, and that appears to be correlated with the PD. Higher number of fires, greater higher that's value PD. The higher temperature, higher PD, higher wind speed, higher PD. But these are individuals, they're not acting together, and we'll come on to that in a minute. Okay, so remember that what I said was we've got these smooths, and in that equation where we said that the smooth was a function of V and the weather, V could be just time, or it could be another variable, or it could be we look at the smooth of the individual variable on its own, and these are looking at the individual variable on its own. So if we look at the coefficient on drought, you can see that the higher is the value of the drought index, and I put a value of 0, which remember to the right of 0 is wetter and left is drier. And 0 here, so above the line means it increases PD, and below the line means it decreases PD. Clearly, if you just regard this as a constant, you will be losing some accuracy. And in the case of fire count, fires, that larger number of fires beyond 10 leads to quite a noticeable increase in PD. Fire right to the right, we may be a bit skeptical for some variables, but in this one, the confidence limits are actually quite tight. Wind speed, that's not the case, but you can see that when wind speed gets above an average wind speed above 8 miles per hour, then PD really rockets up. And for temperature, from about 82 degrees, that increases PD as well. Okay. The other thing that V could be is basically time. So for the drought index, for example, if we look at increasing time, which is on the horizontal, as we increase time, then the coefficient, the effect of drought on PD increases. When we get to large numbers of, over time, the coefficient has gone up. I'm jumping ahead, I'm trying to save too much time. Here, that more recently, the fire count has led to an increase in recent years in PD, and wind speed, it varies a lot. It has varied a lot over time. If we look at the coefficient on wind speed, which I've measured vertically in each case, against fire count, what we see is as fire count goes up, the effectiveness of wind speed on PD gets much, much greater. In the case of temperature, exactly the same. And not exactly the same as kind of inverted U for drought index. If you put these variables together, so you really look at the genuine interactions, think of each of these pictures. Take the one on the left. I've got drought index vertically, and I've got fire count horizontally. So imagine a flat piece of paper, and in one direction we've got drought index and the other fire count. Vertically, we've got PD. And from that base of piece of paper, there are humps and bumps and valleys. And what this picture is showing you are the contours around those humps and lumps and valleys. Okay, so the more red the color, the higher the value of PD. And it's showing the combination, therefore, of fire count and drought, and on the right, temperature and wind speed that lead to these higher values, or indeed the lower values, which are the more blue colors. Okay. So I said I would show you a bit about what would happen if you don't include these variables. So here are a stack of models and the AUC. I'm only going to talk about test, which is on the right. As you can see, we start with a baseline, application variables, property characteristics, duration, time, and geography. And we got an AUC of 77.6. Then when you add in the macro variables, we're up to 82. And then as you progress further down, you can see that when you start making variables subject to the smoothing, then their predicted performance goes up. So, for example, 111B, which is a baseline with smooth spec on the wildfire, you were up to 84.5. Without it, you're at 79. If you make these interactions very smooth, the piece of paper with the multi-colors on, then we get the largest AUC, which is 84.8. We perform statistical tests. I've run out of time to show you, but I can assure you it is statistically better than the other models. Okay, I said I'd say something about capital requirements. I've got a couple of minutes to do that, so here we go. This is a pretty crude, admittedly, exercise, which is why this is work in progress, but I do think it's illustrative. So what we're going to do is we're going to say, let's look at expected loss. Actually, that's a cheat. We're not. We're going to look at PD. LGD, we're going to index as 100%. EAD is going to be $1. Okay. So the scenarios we're looking at are we're taking the Fed's baseline macro forecasts and the Fed's severe macro forecasts and combining that with either a baseline for wildfires and climates, which is the mean of historic values, or severe wildfire climate values. Now, this is where it's work in progress. But just crudely, we take the 99.9 percentiles of the historic values of the wildfire climate variables, insert them into the model, work out the PD, okay, and then we divide that by the baseline. We'll get a ratio. If the ratio is bigger than 1, then at 99.9% of our historic values, we need to have more capital. If it's less than 1, we need less. And here's the result. So we're making a prediction in the left-hand date. So let's think with basic linear model, January 2018. We made a prediction then 3 years into the future. TOR is 3. In other words, in 2020. If we then look at severe expected loss under severe macro conditions compared with the baseline, we get a value of 2, twice as much capital as needed. If we make the wildfire climate variables severe, we get more, 2.24. If we have a combination of both of them, by golly, we need an awful lot more capital, 4.61. Okay. If we look at 2023 relative to 2025, we need a lot more capital. With the smooth functions, which have higher AUCs, if we just stress the macro, we need 3 times the amount of base. If we have stress on combined, then we need 4.7 times much of base. Or put it another way, if you ignore the wildfire climate and other climate variables, and you just stress the macro, okay, you need twice as much capital compared baseline, whereas if you stress both of those, you would need 4.6 times the amount. And of course, you wouldn't want to just stress, take a baseline without stressing the macro. So stressing both is the important thing. And these numbers to me look pretty scary. So there are 2 things coming out of this. The AUC is higher when you include the weather variables, and the amount of capital implied is higher when you include the weather variables. And these conclusions basically say exactly that. Thank you very much. I'm happy to take any questions.
Thank you very much, Jonathan. That's a very sobering capital number at the end. I think obviously a more accurate model is a good thing. A very intricate model, many degrees of freedom. I have a question from the audience, actually. JC, I don't know who it is, but is asking. It's about the depth of the data. We're talking about, say, wildfire events that are very heterogeneous. They have their own, phenomenologically, they're very distinct events. When do we have a large enough sample of wildfires, for example, to make the econometrics stack up? Is there a danger of overfitting to the chance events that have happened so far?
Well, we did use a test sample. So I would suggest that it is pretty robust. Central limit theorem would say you can never have too much data, right? But one has to be realistic. The statistical test that we ran on comparing the AUCs, for example, were very significant. And the wildfire variables were very highly significant, as you could see from just the linear model.
So a strong signal.
Yeah, I mean, okay, so here's the plug. As an academic, we could make this sort of model much better if we had better data. Many academics use the Freddie Mac data because it's very voluminous, but unfortunately it's only at 3-digit level. There are other data sets which are very, very good. By Moody's, there's a BXX data set, which is at 5-digit level, which we don't have access to. And equally, there are probably other weather variables, though we did look pretty closely at all the American agencies we could find for those sorts of weather data for granularity, but there may be commercial data sets that we don't know about. Okay. So if anybody were interested in helping us by giving us more granular data, both in terms of geography, basically in terms of geography, we would look forward to hearing from you.
Okay, well, on that uh, advertising note, or please contact Jonathan directly. But first, thank you very much, Jonathan, for an excellent survey of the weather phenomena and how it affects PD and capital. Thank you very much.